Hi, this is Thomas Vecca, and this is a tutorial for Virtual Cell version 5.1, an environment for modeling cell biological processes developed at the National Resource for Cell Analysis and Modeling at the University of Connecticut Health Center. It is funded by the NIH, and this is a tutorial that uses the conversion of PIP2 to IP3 in order to demonstrate the use of event protocols, functions to better show fluorescence within a cell, and the creation of a spatial geometry using 3D analytic expressions. The first thing you want to do is to take the structure tool and create a new compartment. Then take the structure tool again and create a second compartment. Select the C2 compartment and change its name to nuke for nucleus. Change membrane 1 to NM for nuclear membrane. C1 becomes cyt for cytosol. Membrane 0 becomes PM for plasma membrane. And C0 becomes EC for extracellular. Then with the species tool, click within the plasma membrane twice to create two species. Name the first one PIP2 underscore PM, and name the second one PIP2 underscore PH for pleckstrin homology, and GFP, which is the fluorescence tag, and then underscore PM. And with the species tool still selected, click within the site region to create 4 new species. Name the first one IP3 site. The second one becomes IP3 PH-GFP site. The next one becomes PH-GFP site. And lastly, the last species is STIM for stimulus. And now you've created all the compartments, membranes, and species you need, and it is time to create the reaction. So click on the Reaction Diagram tab, and using the Select tool, rearrange your species so that it's easy to see them all. And this setup works pretty well. And once you've rearranged them, click on the Reaction tool. Select PIP2 in the plasma membrane column and drag to PIP2 PH-GFP. And now you want to add PH-GFP as a reactant in this reaction, so select it and drag to the reaction icon. And now we have 2 reactants combining to form a product. The next reaction we want to create is by clicking on IP3 site and dragging to IP3 PH-GFP. And then we also want PH-GFP to be a reactant in this reaction. And the final reaction we have to create is a stimulus reaction that will cause the production of IP3. So clicking within the white space of the cytosol column, drag to IP3 site. And then selecting the Catalyst tool, select Stim and drag to the reaction. Now you've created all your reactions, it's time to set the rates. Clicking on the reaction in the plasma membrane column, change its name to PIP2PH. Leave the kinetic type as the default mass action, and change KF to 0.12. KR becomes KF, and make sure the K is capital so it recognizes it as the forward rate constant and not a different parameter. And you're going to enter KF times KD PIP2 PH. And then, since KD PIP2 PH is a new parameter, you have to define its value and enter 2 in the expression box. Click on the second reaction and change its name to IP3 PH. Leave its kinetic type as the default mass action and change this forward rate constant to 10. Kr becomes Kf times Kd IP3 pH. And this value becomes 0.1. And the last reaction is our stimulus reaction, which we can leave it as the default name. We're going to change its kinetic type to general, and we're going to change it to K-synth times stim. And now, it's important to note the case here so that it matches the case of your species stim. So that way, virtual cell recognizes it as a species and not a different parameter, which it would have done if it was lowercase s. And then you're going to enter 1 as the value for K-synth. And what this reaction is used is later when we create our first application, we're going to create an event in the protocols that will change the concentration of stim from 0 to 1, which will then make the reaction rate 1 times 1 instead of 1 times 0. And this will stimulate the production of IP3. And so now we've finished with creating the reactions and everything in the physiology, and now it is time to create the application. So click on Applications in the navigation tree, select Add New, Deterministic, and then rename it Steady State. And since this is a compartmental application, you do not need to create any geometry and can head straight to the Specifications tab. If you want, you could reorganize them alphabetically. And now we need to enter the initial conditions for our species. The initial condition of IP3 site is 0.1. We can leave the initial condition for IP3 PH-GFP as 0. PH-GFP site becomes 1. PIP2 PH-GFP's initial condition is 0. And then PIP2 PM's initial condition is 120,000. And stim is also left at 0. And now it's time to go to the protocols in the events tab, and we're going to add a new event. And we'll change its name to act for activation. And then we're going to set the trigger, which is the time when we want the event to occur. And we would want to up the concentration of IP3 when the concentrations have reached a steady state. And it has already been determined that for this model, the concentrations reach a steady state at around 5 seconds. So we want this event to occur when after 5 seconds have passed. And now we have to select the variable we want to use, and we want to apply it to stim, and we want to change its value to 1 at this time. And now we need to add a new event to conclude this, because if we just leave it as this, it will keep upping the concentration of IP3 into forever. And so we'll change this name to inact for inactivation. And we want the first event to last for 1 second. So this event will occur at 6 seconds. And then we're going to again apply it to the stim, and we're going to change its value back to 0. And so now that we've created these two events, in the simulation the concentrations will reach a steady state, and then at 5 seconds the stimulus reaction will be activated and IP3 will be produced, and then at 6 seconds it will turn the stimulus reaction back off, and then the concentrations will be able to reach a new steady state. So now it's time to create the simulation. So we're going to add a new simulation, select edit. We can leave the parameter as the default values and head straight to the solver. The integrator is going to become IDA, and the ending time bound will be 30 seconds. The time step will become, the maximum time step will be 0.01, and then you don't want to press enter to try and finalize the values you're entering, because that will just close the dialog box. You want to wait until you enter in everything. And so under output options, you want to select keep every, and then you want to have keep every 10 samples and at most 1000 samples, and then click OK. And then you can run the simulation. And you want to enter in a unique name so you can save it. And then you can view the running status. And since this is a compartmental simulation, it will be completed fairly quickly. And once it's completed, we can view the results, which will hopefully make it more clear what the events do. So it's completed, and now we can view the results. And as you can see, the concentrations were reaching a steady state, and then at 5 seconds, we activated the stimulus reaction, and the concentration of IP3 was boosted. And then at 6 seconds, the stimulus reaction was turned back off, and the concentrations reached a new steady state, which you can also see how the increase of IP3 caused more PH-GFP in the cytosol to bind to IP3 and less to bind to PIP2. And so this has been the steady state application, and next we'll work on the spatial application. So go click back on applications in the navigation tree, add a new deterministic, and then rename this one spatial. And since this application is spatial, we have to create the geometry. So we're going to go to the Geometry tab, select Geometry Definition, and we're going to add a new geometry using 3D analytic equations. We're going to change the name of the default subdomain to extracellular, and next we're going to add in the cytosol subdomain. So we're going to click Add Subdomain. We want its shape to be a sphere. Its center point will be 555, and its radius will be 5. And then we'll change its name to Site. And at first you won't be able to see the cytosol, because since this is a 3D application, it has slices. So you're going to want to navigate through the slices until you see basically it's almost touching the perimeters of the extracellular region. And now you can see the actual cytosol. Then we're going to add a new subdomain for the nucleus, which is, it's still going to be a sphere, but we're changing the center point to 3.5, 3.5, 5, and then its radius will become 2. And as you can see, here's our nucleus, here's our cytosol, and here's the extracellular region. And another cool thing about 3D geometries is if you click on surface view, you can actually view it in 3D. And if you're having a hard time seeing the nucleus within it, you can adjust the opacity. And now that we've created the geometry, it's time to link the extracellular, cytosol, and nuclear compartments that we created back in the physiology to the subdomains we created in geometry. So we go to Structure Mapping, select the Line tool, click within EC, and then drag to the EC box. Click within Site and drag to the Site box. Click within Nuke and drag to the Nuke box. And it's important to start with the outermost compartment and work your way in as you're mapping. Because if you were to start it from the inside out, you would drag Nuke and then you would drag Site, and it would take the Nuke with it because they build upon each other. So you work your way from the middle out. And next, since now we have to set the specifications, which we're going to do for this application is we're going to start it at steady state, so that way the simulation will be smaller and will run faster. So what we want to do is we want to go back to our first application, and we want to take the concentrations of the species at 5 seconds when they reach their first steady state. So clicking on steady state, we're going to go to Simulations, view results. We're going to view it in table form, and we want to select the following species: IP3, PH-GFP, IP3 PH-GFP, PIP2 PH-GFP, and PIP2. And then we're going to scroll down till we find our time of 5 seconds, or as close as possible in case your time steps didn't have it at 5 seconds exactly, as long as you get a value around that time. And so you want to highlight the concentrations for that row, right click and select copy, and then we're going to go back to the specifications within the spatial application. Right click and select paste all. Choose select all to highlight all the species, and as you can see, it's changing their initial conditions to the steady state concentrations from the first application. And then next thing you have to do is you're going to set the stem to clamp. And what setting it to clamp does is it causes virtual cell to treat it as a constant and not a variable. And the benefit to this is it allows us to set the events here as a boolean, because in spatial applications you can't set events in the protocol. So what you want to enter is 0 plus 1, and then t is greater than 5, double ampersand, t is less than 6. And there was an error somewhere. Oh, 1 times. That's what. And so what this is between times t, between 5 and 6 seconds, the boolean will give a true value of 1. And so then it'll become 0 times 1 plus 1. And for when t is not within that time range, it will give a false boolean value of 0, which is, so it'll be 0 plus 1 times 0, or 0. And then the diffusion constants should be 10 for IP3 site, IP3 PH-GFP, and PH-GFP. And then for PIP2 PH-GFP and PIP2, their diffusion constant should be 0.1. And next we're going to head to the Simulations tab, add a new simulation, select Edit Simulation, and we can leave the parameters as their defaults. And because this is a spatial application, we also have a mesh to worry about. And so we want lock aspect ratio checked, and we're going to change the mesh to 31, and Y and Z will change accordingly to keep proportion. And the reason we made the mesh smaller is so that the simulation will be smaller, and it will be easier for virtual cell to run it. And we found that this is the largest the mesh can be while it's within like the reasonable size limit for a simulation. And we want to leave the integrator as fully implicit finite volume. The ending time bound will be 20 seconds. The maximum time step will stay as 0.1. And then we're going to change the output interval from 0.05 seconds to 0.2 seconds. And then we'll click OK. And the last thing we have to do before we can run the simulation is create a function for fluorescence. So we're going to click Output Functions, Add Functions. We'll name it Fluorescence. And then now we have to enter the expression. And we want to add the concentrations of IP3 PH-GFP and PH-GFP in the cytosol. Click Next. It should say defined in the cytosol by default, but just make sure that that is selected, and then click Finish. And now it would be a good idea to refresh the math just in case it's not synced yet, and then we can select Run and Save. And you can view the running status here. And so while it's running, I'll explain the function some more. What this is, virtual cell reports the concentration of each species separately. So you would see the fluorescence for IP3, and then you would be able to see the fluorescence for PH-GFP. You wouldn't be able to see total fluorescence, which is what you would see if you were to look at this cell under a microscope. And so using this function, we could view what the fluorescence would actually look like in real life, because it allows us to view their concentrations together. And that's usually what the purpose of a function is in Virtual Cell. You're generally using it for fluorescence. And so this is just going to take a couple more minutes to run, so I'm going to pause the video and then resume it once it has completed, and then we can view the results. So the simulation is completed, and now we can view the results. And let's take a time step. We'll start before the steady state. And what you can't see anything yet because we're at the top slice, and you don't really, there's nothing there on the top slice, so you want to get to a slice where you can see a good portion of the nucleus and a lot of the cytosol. And then, as you can see, this is our fluorescence function, which is showing the combined fluorescence of IP3 PH-GFP and PH-GFP. And so as you can see, these are their individual concentrations, but if you were to look at this cell under a microscope in a lab in real life, you wouldn't see their fluorescence separately. You would just see something that is represented by the fluorescence function. And then the last thing that's pretty interesting, and as you can see, when the stimulus reaction was activated, the fluorescence increased in the cytosol because IP3 increased. And so select a point using the point tool and then create a time plot. And this will take a little while to just generate all the data into a plot form. So just bear with VCell, be patient, and so it's almost done. A couple more seconds. And the time plot's really good for seeing how the stimulus changes the concentration. So as you can see here, since we copied the steady state values from the previous application, it automatically starts off at steady state. And then at 5 seconds, when we activate the stimulus, it increases, and then it reaches a new steady state for fluorescence. And IP3 site would probably be the best to demonstrate this with, because that's what we used for the last application, so it becomes a direct comparison. And again, just be a little patient with Virtual Cell. Sometimes it might be slower some days because the server might be more busy. It all depends. And again, it starts off at steady state, the stimulus reaction is activated and then stopped, and then it reaches a new steady state. And this has been the PIP2 to IP3 tutorial.